In the previous video, I introduced you to Newton's third law of motion. In Newton's third law of motion, we consider two objects which are interacting with each other. Newton's third law of motion says that if the objects are interacting, then the forces that the objects exert on each other are equally strong and opposite in direction. One way of saying this is as follows. So let's say I have objects 1 and 2. 1 is exerting a force on 2, illustrated here. 2 is exerting a force on 1, illustrated here. So these two forces are equally strong and opposite in direction. Mathematically, we can say that the force that 2 exerts on 1 is minus the force that 1 exerts on 2. So now we're going to do an example problem which involves two objects interacting with each other. And in this example problem, we're going to be applying Newton's second law of motion to each of the objects, but we're also going to be applying Newton's third law of motion to understand how the objects interact with each other. So here's the problem we're going to look at. I have two masses which are touching each other. The masses are being pushed along a horizontal floor, and specifically what's happening is that we have a finger pushing on mass 1, and the finger pushes on mass 1, then mass 1 pushes on mass 2, and the two masses move together at the same acceleration. That acceleration is rightward and has a magnitude of 4 meters per second, and here I give the values of those masses. We're going to solve this problem by applying our Newton's second law handout to each of the masses individually. So we're going to start by analyzing mass 1. So we can start by drawing a dashed line around mass 1. Then I'm going to come over to the side and make a separate figure of mass 1 here. At this point, I would encourage you to pause the video and do the best you can to draw a force diagram on mass 1 as we've been practicing in the previous videos. So as usual, start by drawing in the gravitational force vector acting on mass 1, then go around the dashed line and use the dashed line to help you draw in all the other forces acting on mass 1. So give that a go, then rejoin the video. Okay, so I start by drawing in the gravitational force vector acting on mass 1. I'll call that G1. Then going around the dashed line, here I can see where mass 2 is contacting mass 1. So mass 2 would be exerting a force on mass 1 going back to the left. So I'm going to call that contact force 2 on 1. As I continue around the dashed line, I can see the finger cutting in through the dashed line. I'm going to call that force exerted by the finger P for push. And the other thing we have here is that the floor is reaching in through the dashed line to touch mass 1. Now, mass 1 is frictionless, so the only force the floor exerts on mass 1 would be a normal force pointing up. So I will call this normal force 1. And I'm not going to put in the magnitudes just yet. Before I put in magnitudes, I'd like to go to mass 2, draw the force diagram for mass 2, and then we can talk about the magnitudes. Okay, so now let's try the force diagram for mass 2. So I will come off to the side here and make a clean figure of mass 2. Then go to the original figure, make the dashed line around mass 2. So try this on your own. Right? Start with the gravitational force vector acting on mass 2, then go around the dashed line over here, look at all the other things that might be exerting forces on mass 2, and draw those forces into your figure as well. Try that, pause the video, try that, and then rejoin the video and see what I do. Okay, so I will start by putting in the gravitational force vector acting on mass 2. Call that G2. Now, going around the dashed line, we can see that the dashed line cuts through the floor, or rather the floor is coming in through the dashed line. The forces exerted by the floor would include the normal force pushing up. I'll call that N2. Then we also have the frictional force that the floor exerts on mass 2. Now, since mass 2 is sliding to the right, the frictional force exerted by the floor would be pointing back to the left. So I'll call that F sub k for frictional force. And then also cutting through the dashed line, we see mass 1 coming in to exert a force on mass 2. And I will call that one the contact force that 1 exerts on 2. Now I'm going to go through and put in the magnitudes. So for gravitational force 1, m1g, the push force, we'll say the magnitude is P. That's one of the things we're trying to find. Normal force N1 over here, and 2. The kinetic friction force between mass 2 and the surface below will be mu k multiplied by the normal force acting between those surfaces, which would be N2. Then we have gravitational force, magnitude m2g. Now notice I have not yet filled in the magnitudes for the contact force 2 exerts on 1 and the contact force 1 exerts on 2. The reason I have left that out is I wanted to make the point that this is an example of Newton's third law of motion here, right? Mass 1 and mass 2 exert forces on each other, which first of all are opposite in direction, as you can see, but also those forces are equally strong. So to indicate that those forces are equally strong, I'm going to use the same symbol C for both of those magnitudes. Okay, so now we have done step 2 in the handout. Next step would be step 3 to draw in the acceleration vector. Let's do that for both of the masses. Now, the two masses have exactly the same acceleration as each other. So for mass 1, I'm going to put in an acceleration vector. I will call that A1. For mass 2, I will put in the acceleration vector. I will call that A2. Now, those two acceleration vectors are exactly the same, even though I have given the 1 and 2 subscripts. And since they are exactly the same, they have the same magnitude. So I will call both magnitudes by just the letter A. So that was step 3 on the handout. Now we go to step 4, which is to introduce Cartesian coordinate systems. Now, in principle, we can give different coordinate axes to each of the masses. But if you look at the figure here, I think it's pretty clear that we want to use standard orientation for each of the masses. So for mass 1, I'm going to come into the figure and put in y-axis pointing up, x-axis pointing to the right, and then same for mass 2, y-axis pointing up, x-axis pointing to the right. And now that we've done that, we can make our grids. So at this point, you can probably just pause the video, make the grids, fill in the grids with all the x and y components, and then once you've had a shot at that, rejoin the video. At this point in the course, I'm assuming we've had some practice drawing force diagrams and making out the grids and filling them in. So before I dive into filling the grids, just take a quick check at the template that I've laid out here and make sure that in your grids, you have all of the forces laid out and also the acceleration vectors as well. And also, because we're doing 2 separate masses, there should be 2 separate grids. So I should emphasize these are 2 different grids, maybe squashed together a little bit more than they should be. So I'm going to dive in now. So we have gravitational force 1, x component 0, y component minus m1g. Push force x component p, y component 0. Normal force 1, we have 0 and 1. Contact force 2 on 1, minus c 0. Okay, acceleration vector pointing in the plus x direction. So x component is a, y component is 0. For mass 2, we have gravitational force 2, x component 0, y component minus m2g, contact force 1 and 2 pointing in the plus x direction. So we have x component c, y component 0, normal force 2, 0, and 2. Frictional force pointing in the minus x direction. So we have minus mu k and 2, y component 0, then x component of acceleration a, y component 0. So that was step 5. Now we're going to go to step 6 on the handout, which is to plug our results into Newton's second law of motion, which says that sum of forces in the x direction equals mass times x component of acceleration, and similar for the y components as well. That's going to give us 4 equations, but we may not need all 4 of those equations. So let's think a bit first about what we're trying to find and which equations we would need to find those things. So we're trying to find the strength of the contact force, right? So the strength of the contact force appears in the x equations for each of the masses. We're trying to find the strength of the push force from the finger, that's P, that appears over here. So we have 2 unknowns, and we're definitely going to need these 2 equations here, namely, we're going to need the x equation for mass 1 and the x equation for mass 2. But as you scan this row here and this row here, are there any other unknowns we're going to need? Well, the other unknown that appears is the normal force on mass 2, and that we can get from the y equation for mass 2. So what we're going to do is we're going to write out the x equation for mass 1, and then the x and y equations for mass 2, and that will give us sufficient information to solve for those 2 things that we're looking for. All right, x equation for mass 1, we have sum of the x components of the forces acting on mass 1 equals mass 1 times the x component of the acceleration of mass 1. So to use this equation, we read across the top row here, add up all the x components of the forces acting on mass 1. That gives us P minus C. Then we have M1. The x component of the acceleration of 1 is A. So this will be our first equation. Then we're going to need the x equation for mass 2. Sum of x components of forces acting on mass 2 equals mass 2 times the x component of the acceleration of 2. So we add up the x components of the forces acting on mass 2. That gives us C minus mu k n2 equals m2. And then the x component of the acceleration of 2 is just A. Call that equation 2. I'm going to box these. And then the third equation we need is the y equation for mass 2. So we have sum of the y components of the forces acting on 2 equals mass 2 times the y component of the acceleration of 2. The y component of the acceleration of 2 is 0. So on the left here, we just need to add up the y components of the forces acting on mass 2. Thus, minus m2g plus n2 equals 0. This would be equation 3. Okay, let's do the algebra now. Or perhaps you pause the video here, try to do the algebra on your own. Remember to work symbolically, obtain symbolic expressions for the things you're looking for, and only then make substitutions of numerical values with units. Okay, just underlining the unknowns and trying to find that contact force C, but I have an N2 also appearing in that equation, but that's okay. I can use equation 3 to solve for N2. So let's do that. Equation 3 gives me N2 equals M2G. So let's take that and put it into equation 2 right here, which then gives me C minus mu K. Here's the substitution for N2. N2 equals M2G. And then that's equal to M2A. Now solving for C, I have C equals mu k m2g plus m2a. Now let's make the numerical substitutions for C. Actually, let me pull out that m2 first. So we have C equals m2 times quantity mu k g plus a. So m2 was 3 kilograms. Mu k, 0.6. G, 9.8 meters per second squared. The acceleration was 4 meters per second squared. So put that in your calculator, and your calculator will probably spit out 29.6. But let's look at the units. So both of those terms in the parentheses have units of meters per second squared, but that is multiplied by kilograms. Kilograms times meters per second squared is newtons, as we would want for a force. So that is the answer, I believe, to part A. Now moving on to part B, that was part B asked us to find that push force from the finger. But now that we have C, the contact force, we can get the push force right away from equation 1. So equation 1, take that minus C, move it to the right, and we have P equals m1a plus C. And now let's make our substitutions. M1 was 5 kilograms. A, 4 meters per second squared. C, we just found 29.6 newtons. We can do a quick unit check. This is newtons. Kilograms times meters per second squared, also newtons. So both terms have units of newtons. And if you put that in your calculator, you'll get 49.6 as the numerical value. And then the answer is newtons. And now we have solved an example problem using both Newton's second law of motion and Newton's third law of motion.